Fine.
Okay, our speaker today is Wolfgang Lück, and he's going to talk about the title you see on the screen, the Farrell-Jones Conjecture for the Hecke algebras or reductive p-adic groups. Please, Wolfgang, over here.
Yeah. First of all, thank you very much for the invitation to give a talk here. I'm aware that Arthur gave a talk about this quite recently, and I will try to complement it as much as I can. Of course, there will be some repetitions, but repetitions are not so bad. I also want to say, if you have any questions, I'm happy to be interrupted. I like to have more talks in interaction than just a talk where no one is asking anything, right? So it's a title, the Farrell-Jones Conjecture for the Hecke algebras. And let me briefly say a preview of what you can expect for the next 50 minutes. So it's joint work with Arthur Bartels from Münster. It's, of course, very important. And our idea is to formulate a version of the Farrell-Jones conjecture for the algebra K-theory, but now comes a new thing. It's about the Hecke algebra of a totally disconnected, locally compact, second-countable Hausdorff group. So we would like to pass from discrete groups to this kind of topological groups. And our main result will say that we can prove it for any closed subgroup of a reductive p-adic group. And this is a very pleasant class of groups if you are working in this area. This is interesting also for people working on smooth representations, as I will try to explain later. And in some sense, Art and I are quite happy about this result because it's kind of exporting methods from topology, coming from equivariant homotopy theory, from algebra K-theory, just to another area, namely actually smooth representations of reductive p-adic groups. So here's a small outlook, what I want to do. I will start with the Farrell-Jones conjecture for discrete groups. So I will probably use 20 minutes just to motivate why this is an interesting conjecture, putting it into a kind of general context. And then I will formulate the Farrell-Jones conjecture in this new setting, where we allow a totally disconnected group. And then I would like to give you some explanations why our proof is much harder than we thought. And sometimes we thought we can do cut zero, and then we can do reductive p-adic groups, but this turned out to be really a much too optimistic statement. And I will also try to motivate the Farrell-Jones conjecture for reductive p-adic groups from representation theory. I will not say much about the actual proofs. They are very technically involved, but try to give some ideas. I may not cover all the slides, but it doesn't matter. You can find them on my homepage. Actually, I would prefer sometimes to stop the slides and give some explanations on an extra sheet besides the slides. And as I said again, please, you are welcome to ask any questions. So let's first of all try to motivate what is the Farrell-Jones conjecture about. So for some time, actually G will be a discrete group. And I assume that you know there are just algebraic K groups for every n element Z. So there's also K minus 1000. They are not the topological K groups you may use to from operator theory. They are the algebraic ones. In dimension n equals 0, they agree, but of course they are very different in other degrees. And the question is simply, can you identify these groups, but now in terms of group rings in more accessible terms? I will later explain why you really want to compute this. And but it turns out that these groups are very, very hard to handle. And in order to get an idea of what could be true, I have to record two things which were actually known in the 60s. So we start with two groups which are torsion-free. So for some time, our groups were always torsion-free. And let's say R is a regular ring. For instance, the integers or the field, whatever you want. Then we know from the Basfeld-Swan decomposition, which is mentioned here, that we can compute the K-theory of R of Z by two copies of the K-theory of R with the dimension shift. That's part of the Basfeld-Swan decomposition. And Stalling proved that, Waldhausen, I should say, not Stallings, but Stalling did it in n equals 0, that if you have the free aggregated product, and you want to compute the reduced K-theory of this, it's again two copies, one copy from G0 and one copy from G1. So these were some basic results from the 60s. But if you are a topologist, this rings a bell. And the bell is that looks like a homology of a classifying space. And here are two statements which are well known and easy to prove. Suppose you start with some generalized homology theory. Could be singular homology, could be Bordism theory, whatever you want. But they all share the following formula. If I want to compute the homology of B of Z, I get two copies of the homology of a point, again with the dimension shift. And if I compute the homology of the free product, I do get two copies of the homology of G1. And I think it seems to be clear that these look pretty much alike, as this and this look pretty much alike. And this, of course, raises the following hope. When you're optimistic, and we are optimistic, is it possible that this very hard to compute group is always given an expression like this? So you apply homology to the classifying space of PG, where you, of course, you have to find the right homology theory HN. But of course, this has only chance to be true if G is torsion-free and R is regular. And actually, let's make a reality check. If this is true, it should be true for the trivial group. But this tells you that the homology must have the property that when you apply it to a point, it must be the algebraic K groups of R. But now as a topologist, there's an immediate candidate because algebraic K theory is given in terms of a spectrum, whatever that is. But when you have a spectrum, you get an homology theory assigned to it with this property. So our candidate is actually there. And even better, there is already a map defined by Lodé, which relates the homology of BG with this spectrum as coefficients to the algebraic K theory of RG. So a map is always there. They have the candidate. And now your hope is simply that this map is an isomorphism whenever your group is torsion-free and the ring is regular. And I should also say for the applications I would like to mention, besides algebraic K theory, there's also algebraic L theory, whatever that is. That is the analog of K theory of quadratic forms and plays a big role in surgery theory. And we need surgery theory for the explanation of the applications I would like to explain next. And everybody has his favorite conjecture. I have about 3 or 4 favorite conjectures, but in manifold theory, this is the Borel conjecture, which I like most. So let me explain it, what it says. We first of all have to figure out what this here means. So we call a manifold N topological rigid if any homotopy equivalence from any other closed topological manifold M to N, which is homotopy equivalence, is actually homotopic to homeomorphism. That is an extremely strong statement, right? Whenever you have two spaces and you have a homotopy equivalence between them, there's absolutely no reason why these spaces should be homeomorphic, and even there's less reasons why any homotopy equivalence you can see comes up to homotopy from a homeomorphism. This is a really very strong statement. And the Borel conjecture tells you that this property is shared by any aspherical closed manifold. What does aspherical means? It means that universal cover is contractible, for instance, you may say that. And the class of closed manifolds, which are aspherical, is really huge. It contains all remaining manifolds of non-positive section curvature. Many 3 manifolds are spherical. So this is really a large class of prominent manifolds, and they all should be topologically rigid. And as I say, this is really very surprising. In particular, it says, if the Borel conjecture is true, that when you have 2 aspherical manifolds, and you want to decide whether they are homeomorphic, you just have to check that their fundamental groups are isomorphic. So the fundamental group sees the complete manifold up to homeomorphism, what is again in general completely unlikely. For instance, there are many simply connected spaces with trivial fundamental group, which are not at all homotopy equivalent or homeomorphic or whatsoever. And the interesting thing is, this was the Farrell-Jones conjecture about K-theory and L-theory, which doesn't seem to be linked to the Borel conjecture, but the Farrell-Jones conjecture does imply the Borel conjecture in dimension bigger than 5. And it does it also in dimension 4 if your fundamental group is good in the sense of Friedman, but I will not talk about low-dimensional situation in this context. So this is for me one of the striking examples of the Farrell-Jones conjecture, and there are many more. And I can imagine that many of you know this already. So let me briefly go through the list without any comments. So what are conjectures which are implied by the Farrell-Jones conjecture? It is the vanishing of the K groups in dimension n less equal to 0 of integral group ring and of the vital group if G is torsion-free. We have the prominent Novikov conjecture. There are conjectures due to Bass, to Moody, to Serre. There are many applications when you want to classify manifolds. There are applications to Poincare duality groups, to K-classes of spherical manifolds. There's a question coming from geometric group theory, whether an hyperbolic group, which boundary is a sphere, is actually coming from a manifold. And rational computations of the homotopy groups of spaces of automorphism of spherical closed manifolds. And together with Ferry and Weinberger, we were able to prove a stable version of the Cannon conjecture in dimension 3. Of course, the Cannon conjecture is still open, but the stable Cannon conjecture comes very close to a solution. So there are many, many other conjectures, and very often the story goes as follows. You want to prove this conjecture, Novikov conjecture or Serre conjecture, whatsoever. And if you can prove the Farrell-Jones conjecture, you get this conjecture as well. But there are very often groups for which these conjectures were not known before, but the Farrell-Jones conjecture could be proved for these groups. And therefore, even you are not interested maybe in the Farrell-Jones conjecture, proving it has many, many applications to operator algebra, geometric group theory, and the classification of manifolds. So, of course, we had this condition that G is torsion-free and that R is regular. I made this just because I wanted to look at the, on the first glance, rather, let's say, easy map from the homology of BG to KR to Kn of RG. But what is the general formulation? This is slightly more complicated, and we will not really need its precise formulation, more or less that it exists, but I would like to indicate what you really do. So what you have to do if G is arbitrary and R is arbitrary? We still want to compute this. And now there's a multi-theory. When you take a point and plug it in, you get this here. And then there is this space here. And this is the classifying space for the family of virtually cyclic subgroup. I will not go through the details, but you should recall that the group is called virtually cyclic if it is either finite or it contains Z, the group of infinite cyclic group, as a subgroup of finite index. And then you have again the statement that this map is an isomorphism. And the game we are playing is always the same. We want to compute this. This is very hard, and this is much more accessible. So, and here I rephrase what this really is. Here now you have to plug in a geomorphism theory. This is an homology theory where you put G in front of everything and you have a right definition. But now its values, you have to do it for any homogeneous space. And there you get really what you want, namely the K-theory of R of H. For the homotopy theorist, that's the spectrum version of it. You want to compute the value of a functor for G in terms of a big homotopy colimit, but you only take those subgroups into account which are virtually cyclic. So the game of the Farrell-Jones conjecture is always the same. You want to compute a functor defined for a large group G in terms of very nice subgroups of G, for instance, finite subgroups or virtually cyclic subgroups.
So, sorry, when you write G over V or Z over G, you mean the groupoid algebra of that, right?
No, that's the homogeneous space, G mod H. So when you have a group G, you can have a subgroup.
Okay, so KR is the K homology.
Yes, right. Actually, I would like to go to the Baum-Conn conjecture, so then you are with your unfamiliar terms. So I assume that you have seen the Baum-Conn conjecture, most of you. There you have Kasparov KK theory, a space which people call sometimes E underbar G. And then there is a map to the K theory of the reduced groups to star algebra, right? And if you go through this kind of constructions I've done here, this is a kind of homotopy theory, which for topologists is given by plugging in this space E underbar G, and you need a certain spectrum. I will not specify this. And this turns out to be isomorphic to Kasparov's KK theory. And if you plug in here the value of this for G mod G, then this turns out to be isomorphic to that. And the assembly map in the type I've described before corresponds to the one of Farrell-Jones. So this is via homotopy theory. And this would be via index theory, but they can be identified. And this E underbar G, which is called sometimes the classifying space for proper group actions, is just what I would call, in this context today, the classifying space for the family of finite subgroups. So you see in some sense that this here is in the same spirit as the Baum-Conn conjecture. But of course, you have to look at other coefficients in the sense, other theories. You change this to the algebraic K theory, to the topological K theory of the C-star algebra. And if you change this, you have to change this entry here, and you have to change the family, and then you get the Baum-Conn conjecture. Does it answer the question roughly?
Yeah, I mean, so you are using KR of G mod G for H upper G, G mod G with coefficients in KR. So,
yeah.
That was my question.
Okay. Very briefly, you see, when you have a nice conjecture which has many applications and you can't prove the conjecture, that's not very convincing. But with the Farrell-Jones conjecture, the situation is actually rather good. I think it's fair to say that a lot of work was done by Arthur Bartels and myself, but there are, of course, other people who contributed to this list of groups where the Farrell-Jones conjecture is known. So prominent one are hyperbolic groups. And I think very important with a lot of application is we can prove it for all Cat0 groups. We can prove it for solvable groups, and we can prove it for all lattices in almost connectivity groups. Actually, it can be any lattice in any second countable locally compact Hausdorff group. So more or less for all lattices you see. It's true for all low-dimensional manifolds, the fundamental groups. It's true for all arithmetic groups and all mapping class groups. So this is a very good class of groups and becomes even larger because we have very nice inheritance properties. For instance, it's closed under products. So the class of groups for which the conjecture is true is closed under products. It passes to subgroups. And this is in some sense also known for the Baum-Conn conjecture. But what is new in our context is it passes to overgroups of finite index. So if you have a group G and a subgroup finite index, and you know the Farrell-Jones conjecture for the small subgroup, then you know it for G already. And very important is this here. So when you have a directed system of groups, and now comes a point with not necessarily injective structure maps. So I'm not talking about G to be a union of subgroups. Then you may look at the colimit. And if each GI satisfies the conjecture, the same is true also for Fj. The reason why this is interesting is the following. Nigel, Hickson, and Skandalis and Laforgue found counterexamples to the Baum-Conn conjecture with coefficients as soon as you have one of the Gromov monsters. And the Gromov monsters are constructed as colimits over hyperbolic groups, but the structure maps are always surjective. They're not injective. And turns out that such groups exist, and there are counterexamples to the Baum-Conn conjecture with coefficients. But we also know that any group which is constructed as a colimit by hyperbolic groups satisfies the Farrell-Jones conjecture. And a lot of interesting groups with bizarre properties, which were constructed by the geometric group theorists, are actually constructed in terms of colimits of hyperbolic groups. That is the reason why at the moment I have no candidate for a group for which the Farrell-Jones conjecture makes me nervous. I'm not claiming it's true for all groups, but if I should mention a property which makes me nervous, I have no property. For instance, for the Baum-Conn conjecture, there were times where people thought that Cashtan's property T could be a barrier, but then of course Laforgue went beyond this barrier, and so on. The Farrell-Jones conjecture is open for out of n, and now comes maybe a point which is interesting for people working on the Baum-Conn conjecture. It's open for amenable groups. So if you know Brightson's universe of groups, I don't know whether you've seen this. He draws it like this. These are the finite groups. I hope I do not offend anybody. Then you have something going on here, going on there. And this is solvable, amenable, and so on. This is free, hyperbolic, and automata, and here alliance. Here you know nothing. And the Tarski and the monsters of Gromov, they all lie here. But it turns out that at least the Farrell-Jones conjecture is known for them. And you can say, roughly speaking, Farrell-Jones is very good here. Baum-Conn is very good there. Farrell-Jones is a little bit weak there. And Baum-Conn is weak there. So in some sense, it has to do that the methods of proofs are so different. In the Baum-Conn world, you can use analysis. And in the Farrell-Jones context, you can use more geometry. Okay, this is the first part of the talk. So are there any immediate questions? And I would now go on to the new results.
I was just going to ask, what's the status of the question about Farrell-Jones for amalgamated free products? So those are examples of colimits, but...
the problem is the following. If you would allow field coefficients, then it's no problem. But if you have if the free amalgamated products are not a problem, but if you have free amalgamation over a subgroup, then we do not know. It is, for instance, known for the Baum-Conn conjecture. When you have amalgamated product, G1, G2, and G0 in the middle, and you know all of the Baum-Conn conjectures with coefficients for these small groups, you know it for the product. That is due to Juno, I think, but this is not available for the Farrell-Jones conjecture. The reason is that we have nil terms, which you do not see in the connection with Baum-Conn. Right. I may say more about this later.
Yeah.
Sorry, yeah. Actually,
question also. Do you have also a version of the Farrell-Jones with coefficients, as in system algebra?
Yes, I have put under the rock. Actually, our coefficients can be any additive categories. And this is the reason why we get these nice inheritance properties. If you would only use a ring, like in Baum-Conn, if you would only say, I want to have it for the complex numbers as coefficients, there is no inheritance. But for the Farrell-Jones conjecture, if you go to additive categories, like in Farrell-Jones, you get these nice inheritance properties. Yeah.
But isn't, I mean, so equivariant homology with coefficients in an additive category, isn't it the same as the same homology with coefficients in a ring associated to the category?
Yeah, that's we do. We would actually, I think I have
a non-unital ring.
No, I didn't. Let me go to the right here. So what you can do is, there was a spectrum K of R, if you remember, right? And you can replace this by a spectrum where you put in an additive category. An example of an additive category is the category of finite generated projective modules over R. So this really generalizes what you're doing there. And if you allow additive categories, then you get all these nice inheritance properties.
Yeah.
It's only... Yeah?
What I was saying is that you take, I mean, you have this additive category and you take the direct sum of all the homes and you get the ring.
Yeah, but I wouldn't recommend to do this. But
And
it
the
is,
effects are equivalent.
yeah, that's true. But I mean, was an issue when you want to define sister algebras of a category, right? You can do this also using this kind of rings. But yeah, you can do it, but it's easier to work with the K-theory of an additive category because then you can do word by word the same as you did for rings without any thoughts, right? Because K-theory is defined for additive categories without any harm, actually, for more general situations.
Okay.
Okay, so let's, before I come to the p-adic groups, one point which also shows how parallel this is to the Baum-Conn conjecture. As I mentioned, this kind of virtual cycle subgroup, that is pretty bad family in some sense. It contains some infinite subgroups. And I would like to stick to finite subgroups as you can do in the Baum-Conn conjecture. But this is also possible for Farrell-Jones, but then you must look at fields of character 0 as coefficients. And then you have this assembly map, and this is also an isomorphism. And this looks now exactly as it looks for Baum-Conn. Remember, in Baum-Conn, on the left side, you have also this space Efin G occurring. And Baum-Conn, since you're working over sister algebras over C or R, is of course something which corresponds to have a field of characteristic to be as a coefficients. So this is now the main, yeah?
The left-hand side is the same if you replace K by KH, right?
Yeah, yeah.
So the conjecture would say that the right-hand side is also KH. So it's that FG is
Let's say K, so what do you say what do you mean with KH?
homotopy algebraic K-theory. So that the
Oh, homotopy, yeah, that you can also do. You can formulate the Farrell-Jones conjecture for homotopy algebra K-theory, then you will always get the conjecture in this form. But the reason is in homotopy K-theory, you threw away all needed terms, right? That's the idea of homotopy K-theory.
Yeah, but what I mean is that the left-hand side here is the same. If you put KH, it is the same because if
it's the same. Yeah, that's true. Yeah, that's true. Yeah.
So the assertion is that you could think of it as saying that the conjecture with KH as coefficients is true, and in addition, that FG is K regular.
Yeah. Of course, we also thought about proving the Farrell-Jones conjecture directly to KH, but what we can only do is if you know the Farrell-Jones conjecture for algebra K-theory, then you get the conjecture for homotopy K-theory with finite here for free, but not the other way around. So there are a few instances where you could prove the theory for homotopy K-theory directly. For instance, then it's much better behaved when you have free aggregated products. Then you have kind of inheritance. But usually when you want to prove something, it's not an advantage to put in the homotopy K-theory. Most of the applications go like you prove it for K-theory and then you get it for homotopy K-theory for free. This is what I experienced.
Okay.
Okay,
So,
but yeah.
Small question. So if you take the complex numbers, so you say the left-hand side is the same as the Baum-Conn left side?
No, then you have to change the theory from algebra K-theory to topological K-theory.
It's not the same. Okay.
It's not the same. Maybe at the end I will say about it. The point is we have a kind of meta conjecture, which says you give me a certain functor from groups to spectra whose homotopy groups are algebra K-theory of the group of topological K-theory, TC, THH. Then you can write down an assembly map, and the meta conjecture tells this assembly map is an ISO. And if you now choose this kind of functor according to your theory, Baum-Conn, Farrell-Jones, TC, HH, then you get the corresponding conjectures of Baum-Conn, Farrell, and Jones, and so on. This is very important. Maybe at the very end, I want to mention that Baum-Conn and the L-theoretic Farrell-Jones conjecture, if you invert two, are the same. It means a kind of comparison maps, and this can be done if you have this global picture, right? Where the theory is decided by the choice of the coefficients, but the rest is very similar.
So if Baum-Conn and Farrell-Jones conjecture is true for some group, and so this doesn't mean that the algebraic K-theory is the same as the topological K-theory of the...
In some sense, yes. It would then say, but it's the L theory, by the way. It would say, maybe this is what the claim is. The L theory, sorry. The L theory, let's take R of G, where you invert 2 is isomorphic to KO of the reduced group C star algebra with R coefficients. And this is really algebraic L theory.
What do you mean by C star algebra of G with coefficients in R?
Or just the function from G to R, real numbers.
You
These
take the real numbers.
sorry, the real numbers.
Okay.
I don't want to go to complex numbers, and this is not true anymore. And this would be the topological K-theory. So the real topological K-theory. Here I'm talking about the real numbers, yeah.
It's real C star algebra then.
Real C star algebra, yeah. And this is a very interesting connection. If you believe in roughly speaking, if you believe in Farrell-Jones in Baum-Conn, there should be an ISO. If you could prove this map, there is a map from the left side to the right side to be an ISO, then Farrell-Jones and Baum-Conn would be the same. So this is a very interesting project. Actually, sorry, I'm digressing now, but for me, all these questions, what is true for the Baum-Conn conjecture? For instance, the Baum-Conn conjecture for the Banach algebras is much more often true than the one for the C-star algebras. I propose, together with Nigel and Arthur, to look at, for instance, the Fréchet algebra. There's always the change of theories map, which would be interesting. And if one could get information about these, you would get some interesting consequences. For instance, I view the examples of Nigel, Scandalis, and Laforgue, these counterexamples to the Baum-Conn conjecture with coefficients. They tell me that the Banach algebra, its K-theory, is not the K-theory of the C-star algebra. Right. So this is a different point of view, which could be interesting in the future.
Yeah, thank you.
Okay, now let's, so having this here in mind, I now can formulate the Farrell-Jones conjecture for totally disconnected groups. So now for the first time, we're looking at a 3D group. And I have now to use a uniformly regular ring. I won't say what uniformula means. Suppose R is a field, then you are in business. This is a technical condition which we probably not need for the theorem to be true, but our proof requires this. So I'm looking at the regular ring. So that Q is contained in R. That's important. So at the moment I have excluded the integers, but that is not a surprise. And now we have an assembly map. Now compare this, and COM means compact open subgroups. Now, if you think about the discrete groups, what are the compact open subgroups of a discrete groups that are the finite groups? So if you want to look at TT groups, the natural, let's say, generalization of finite groups are compact open subgroups. And now formally you have the same thing. This assembly map is the projection from this classifying space to the G mod G. And G mod G is exactly what you want to compute. But now notice we change from K and f of G to this expression, which I have to explain. And here's the point. This is again a smooth geomorphism theory. Smooth means it digests those spaces which have open isotropic groups. So whenever I will say smooth in this talk, I mean open isotropic groups. And this theory has a property that if you plug in G mod H, where H is an open subgroup, you get the K-theory. But now you're looking at the Hecke algebra of H with coefficients in R. I will say later more about it, but you should think about the Hecke algebra of the natural generalization of a group ring of a discrete group to a kind of group ring for a totally disconnected group. So the Hecke algebra plays a role of the group ring. And now you see that formally, this is pretty much the same as we had before. And I made this conjecture actually, I think 20 years ago, and this year we could prove it. And our theorem is that this map is an isomorphism if G is a closed subgroup of a reductive p-adic group. So I want to point out that G is not, can be a subgroup. That's interesting. I will explain later, of a reductive p-adic group. People work in representations theory. They want to understand these groups. And why this is linked to representations theory, I will explain a little bit later. But now let me give you a kind of dictionary so that you can a little bit appreciate or understand the passage from discrete groups to TT groups in some sense. So you know what the G representation over R is, that's defined algebraically. And if you pass to T groups, you have to look at smooth G representations. And these are just representations of G over R, but they are smooth. That means that all isotropic groups you see are open. For discrete groups, you have the group ring, and this is replaced by the Hecke algebra. By the way, what is the group ring? It's more or less the function from G to R with finite support and the ring structure coming from convolution. And this is the algebra of functions from G to R with compact support, which are locally constant. That is the main point. And the ring structure comes from convolution again. But the Hecke algebra is much more complicated. The group ring always has a unit. The Hecke algebra doesn't, but it still has an approximate unit. That's the same definition as you are used to when you're working with the star algebras. And that is the best you can get if you have no unit. And what you probably know is that the category of G representations is just the category of RG modules. That is identically the same. And the same holds on the left side, but you have to add smooth. And you have to replace the group ring by the Hecke algebra. And ND means non-degenerate modules, because we have no unit, you have to say that. So roughly speaking, modules over the Hecke algebras are smooth G representations. And G representations which are smooth, that is what people really want to understand. So I won't say what the reductive p-adic group is. Examples are GLNQP and SLNQP. And on the discrete side, this is something which we would call a cut-zero group. And examples of a cut-zero group are fundamental groups of closed manifolds with non-positive sectional curvature. And in the case of a cut-zero group, it comes often with a very nice co-compact action on a cut-zero space. And this has a very nice analog in the case of a reductive p-adic group. You have the so-called Brouwer-Titz buildings that are simplicial complexes with very nice geometric and combinatorial structure. And they have a co-compact proper smooth action of such a reductive p-adic group. And this is the reason why we were trying to extend what we did for cut-zero groups to this more general setting by looking at this action. And I said already, the final groups are now to be replaced by compact open subgroups. And in some sense, the situation looks to be discrete, but it turns out to be much more complicated, although many of the ideas we had, of course, for discrete groups could be used again. But I would like to give you three reasons why this is really more complicated when you pass to the totally disconnected world. Here's a very simple observation. Suppose you have a finite group F, and you have a descending sequence of subgroups. It stabilizes. The order has to go down or is constant. This is not at all true in the TT setting. Think of the p-adic numbers. There's the perfect compact two disconnected groups. And now you can look at p times the p-adics, p squared times the adics, p cubed times the adics, and this goes on and never stabilizes. For homotopy theory, the really bad thing is the following. When you have a discrete group and you look at GH cross GK, which is the diagonal action, that's important. Then, of course, this is the disjoint union of its orbits, and therefore it's a zero-dimensional GCW complex. This is something you use, you never think about it. But exactly this is not true in the TD world. If you look at the space GH cross GK, with the diagonal action, that's important. There's not even a homotopy equivalent to a GCW complex, and this causes a lot of problems. And in some sense, 61%, I'm kidding, of our problems are coming from this fact. Another point which makes it harder is in the discrete world, there are versions of classifying space of families, a CW version, and a numeral version. I will not give the definitions, and they agree. But in the TT setting, these are different spaces, not even homotopy equivalent. And you have to make a decision whether you want to work with these pleasant spaces concerning equivalent homotopy theory, or with these spaces which have other big advantages. But you will not be able to exploit both properties because they are not homotopy equivalent. Fortunately, if you plug in the family of compact open subgroups, they agree. But the main issue in our proofs is actually that we have to allow non-open subgroups in between. And this is really the new innovative thing about our proof, which could also be interesting for representation theory. I will say more about it maybe later. And here another typical problems. And the group ring is functorial under group homomorphisms, right? If we have a map from G to G prime, it uses a ring homomorphism from RG to RG prime, and therefore also a map from the K groups of RG to the K groups of G prime. No problem. But this is not true for the Hecke algebra. It's only functorial under open group homomorphisms. Open more or less means the kernel is open. So Hecke algebras are not functorial under inclusions of subgroups unless H is open. But as I said, we will be forced to look at non-open subgroups, and there we didn't even know what is a K-theory because there is no way of defining the K-theory of H in terms of Hecke algebras and be able to compare it with the big one. This is a very complicated issue, and it turns out that what we are defining will depend also on how H lies in G. That is an important thing. I mentioned already unit. So unit actually is there if only if G is discrete. And in this theory, I want to make this point here also, that when you're looking at reductive p-adic groups, there are some very interesting closed subgroups which are not necessarily open. Think about the Borel subgroups or whatsoever. And even if you start with reductive p-adic groups, these groups may not be necessarily reductive p-adic again. But if you think about the keyword Jacquet functors, you will see that you really want to compare K-theory of a reductive p-adic group with certain subgroups which are not open again. That doesn't make sense on the right side because any subgroup of a discrete group is open. So you not think about this. Okay. So we have now a conjecture. So again, the pattern is, again, you want to compute this, the K-theory of the Hecke algebra. You want to identify it with a certain homology theory evaluated as a family of compact open subgroups. So roughly speaking, you want to compute this in terms of the values where G runs over the compact open subgroups only. So why is this interesting? You see, I mentioned the Borel conjecture, but for TT groups, there is no manifold theory. So the applications, if there are any, are of completely different type. And the most applications I know are about representation theory. And here is a very prominent one. That's the famous result of Bernstein and Dat I've mentioned here. So they started with a reductive p-adic group, and they wanted to compute K0 of the Hecke algebra. So in representation theory, you always want to understand the projective class group, which plays a role of the representation ring, roughly speaking. And they could say that this is a colimit where you look over all compact open subgroups of G, and there's a map from here to here because K sits in G and you have an induction, and this should be an isomorphism, and they can show it rationally. So if you don't like colimits, you could also do the following. You place a colimit by all possible compact open subgroups, and then this map should be surjective. So everything you have in the K-theory of the class group comes by induction for some compact open subgroup. That is the idea of this conjecture. Their proof uses everything that was known at the time about representation theory. But now we can get a much better result, namely, we can weaken the condition reductive p-adic group to a closed subgroup of such an object. the complex numbers can be replaced by our standard assumption that are uniform regular rings satisfying Q and R. And the main point is that we drop this here. So we can show that this map, which computes the K-theory of the Hecke algebra in terms of compact open subgroups, is integrally in isomorphism for many more rings and also for closed subgroups. This is very interesting because Dat actually made conjecture that it may be possible this map is surjective, and he wrote a sequel of several papers where he investigated the possible co-kernel. But now we know the co-kernel of this map is just trivial, so that is now a better explanation for the results he was getting. But I should be honest, they did it only using representation theory, and we had the advantage that we have a completely different arsenal of methods available to address this question.
All right.
Here's another a result due to Schneider and Stuhler. They looked at so-called admissible smooth representations over a reductive p-adic group. Admissible means essentially that all fixed point sets of compact open subgroups are finite dimensional. And then they could show that any such representation has a final projective resolution. And now comes the point by compactly induced modules. So in other words, the representation itself is not compact induced, but it has a resolution by objects. Each of it comes from some compact open subgroups. And our result actually says, roughly speaking, we can drop this. This is interesting because it's the best you can get. Of course, we still need finally generated, but if we have something which can be resolved by finally generated projective modules, it should be finally generated from the very beginning. Otherwise, you have no chance because the map from P0 to this module is surjective, and if this P0 is finally generated, P0 should be finally generated. So this is another application to representation theory where we can prove more than it was known before. And here is one point which is very interesting, which we cannot really prove, but is a really interesting conjecture in the theory of representations. It's a conjecture which is attributed to Bernstein, although Bernstein told me he never made it, but everybody calls it the Bernstein conjecture. And he is looking at a very specific representation. So he fixes a group and looks at an irreducible, and now comes the notion supercuspal representation, whatever that is. And he asks whether this representation comes from some compact open subgroup and representation over this, and then he deduces it up. So roughly speaking, the basic building blocks for representation, these irreducible supercuspal ones, they all come by induction from compact open subgroups. And my colleague, Jessica Finson from Bonn, I think has made substantial progress about this conjecture in the recent years. And our result, you may view as a kind of K-theoretic analog, but proved in much more generality. But K-theoretic analog has one grain of salt. Our construction is, of course, not explicit. Jessica is able to start with such a representation, and she can figure out the compact open subgroup in some sense. Actually, she can figure that out and actually gives a candidate for the representation. So we can only roughly say that up to isomorphism, any element which is a representation over the reductive p-adic group is more or less compactly induced. On the other hand, our result is much more general because Jessica really has to stick to coefficients in the complex numbers. And that is something we have to understand. So I'm not claiming that our conjecture implies the Bernstein conjecture. There are relation between them. There is a kind of program how one could get very close, but at the moment, I think we have nothing to say about whether the Farrell-Jones conjecture does imply the Bernstein conjecture. Yeah, actually, I have now talked for 50 minutes. So maybe we should ask questions first, and then if I have time, I can say something about the proofs. Thank you.
Thank you, Wolfgang. So are there any questions?
Maybe I can ask a question about cyclic homology. So the analogs of this Farrell-Jones conjecture in cyclic theory are much easier and been known for a long time. Can you comment on what makes the Farrell-Jones much harder than its cyclic theory counterpart?
Here's an example. If you look at Hochschild homology, very easy. Hochschild homology more or less decomposes according to the conjugacy classes of elements. You may have seen this. And this is a Farrell-Jones conjecture already, more or less. So for instance, for Hochschild homology, Marco Borisco, Rochnes, and I proved this in a very easy way that the Farrell-Jones conjecture is true. The problem is that for the K-theory, when I would have to go into the proof, you have to construct certain transfer maps, which do not occur when you want to prove it for cyclic homology. There you use more or less Chern characters and other things as a detection. And this makes it so more complicated. It's just due to the different theory. That's all I can say. So you see, I view always TC, I mean topological cyclic homology or cyclic homology, as approximations of K-theory. K-theory is really the thing we want to compute, and you will like to map it to something which is easier. And these kind of theories like TC or complex cyclic homology are just easier to handle than algebra K-theory. That's all I can say, roughly. Sorry.
Thank you.
I have a trivial question. If you gave the definition of uniform irregular, I missed it.
Yeah, I didn't give it. I can tell you it's easy. A ring is called regular if it's Noetherian, and any defined module has a resolution of projective modules of dimension d. And d may depend on the module. But uniform means that d is a fixed number, which is the same for all modules.
So it has finite homological dimension.
Yeah, in some sense, that is enough. If you have a ring which is Noetherian and has global finite dimension, it's also uniformly irregular.
Okay, thank you.
But I think uniform is a kind of condition we need for technical reasons. I think it should be used, but our proof does rely on it, unfortunately.
So
I have a question.
oh yeah, please go on.
Yeah, so my question is, can you state this Farrell-Jones conjecture also for topological algebra? So say you want to plug in the Schwartz algebra for reductive p-adic group instead of the Hecke algebra. Do you get any information there?
I do not know. It's a very good question, but I had not thought about it. Because there are other algebras you would like to. I mentioned already Frichet algebras, but the Schwartz algebras are important. But I have not thought about it. It's possible, but I have nothing to say at the moment about this. But it's a good question.
Okay, and also, does it matter if you take, say, well, non-Archimedean topological algebras? So instead of the Hecke algebra, take the Banach Hecke algebra. So the objective would then be to study things like locally analytic representations.
I had not checked this, but at the moment, I think the proof of it written down uses really to look at the Hecke algebra itself. Because there are certain transfer maps which we are constructing. This is a hard part. And there I would have to think really in detail and for some time where this generalizes to your setting. But again, it's an open successor project for this year.
Are there any more questions? Okay.
I have another one.
Okay.
Yeah, so are there cases where you can prove the Farrell-Jones conjecture for homotopy algebraic K-theory and you don't know something about algebraic K-theory in general?
Yeah, there are two things. I think we can show when we work with homotopy K-theory that it is when you have an action of G on a tree, and all the stabilizers satisfy the homotopy K-theory version, then also the big group. That is what is known for BOM-con, something Oyono, that we can prove only for homotopy K-theory. But the reason is that in homotopy K-theory is for me only an image of K-theory, right? So homotopy K-theory is K-theory without the problems concerning Nil terms. It is good to have it, but I really want to understand K-theory, right? But in most applications are of the shape that if you know the Farrell-Jones conjecture for K-theory, you get it for homotopy K-theory for free.
I see.
In relation to this, when you have a non-Euclidean ring and you want a condition that ensures that the ring be K-regular, so that its algebraic K-theory and its homotopy K-theory be the same. So a condition is that it be regular supercoherent, where regular means what you explained without the Noetherianity assumption, and instead of Noetherianity, you ask that it be supercoherent, meaning that the category of finally presented modules is abelian, so it's stable in the kernels and co-kernels.
Yeah.
And that this is also true, the super means that this is also true for polynomials on R, in any finite number of variables. So does this, do these properties appear somehow in any of these? So like, I mean, you can show that R of G has this property, for example, when it's obviously
Yeah.
Noetherian.
Okay, let me give you one hint. You see, we can prove the conjecture for we want to prove the conjecture for compact open subgroups, right? And here you have all subgroups, and immediately you have all virtually co-virtually cyclic subgroups. So these are all open. These are not necessarily open. And this gives you what we want. And we can actually show that this is an isomorphism without any conditions on the ring R. So this is true always. The problem is, and which is much harder here, is this passage there. And this means, for instance, that you want to compute the K-theory of a Hecke algebra of this shape. So you have a compact subgroup K, and Z acts on it. And now you look at this group K cross Z, and you want to compute this K-theory. And we can, for instance, show that this is 0 in negative degrees. This is related to this question, of course, whether the ring is regular. And this is the key input why we can finally show that this is also an isomorphism. So questions like you are asking, whether we can get rid of Nil terms or whether things stay the same when you pass from R to the R of Z or R adjoint polynomial, that we have to go in when you want to do this thing here. So we are dealing with these questions. By the way, the Hecke algebra is always Noetherian. This is a big theorem of Bernstein. And since you have this nice action on the Ruber-Titz building, you often have also very nice projective resolutions of some of the modules. So that is the good news here. But we have to deal with these questions. They really occur. So when we want to compute the negative K groups here, then it becomes relevant to look at these things. We have to go through Barcelos-1 for additive categories where you have twisted, even twisting, where you have Nil terms. And for us, very good was the notion of a regular coherent ring. I think you know what it is, where you drop regular, where you drop Noetherian.
Yeah.
Noetherian is something we can't use. The reason is, at one point, we have to look at infinite products of additive categories. And an infinite product of additive categories is never Noetherian if each entry was Noetherian. So our main technical thing was not to use Noetherian. And there we could get along by a regular coherent, and that works after a lot of efforts, I must say.
So have you, because on a different project, I was looking for literature on coherent rings, and I mean, the papers I found are all from the 70s or earlier.
Yeah, he has one problem with
Produced-
regular coherent. Yeah, he has one big problem, which is an open conjecture. If you have a regular coherent ring R, we do not know whether R of Z is regular coherent again. That's an open question. If you would have this, we would have had a much easier life.
I know. I know. I mean, I read somewhere that this is not true if you just add T, not T and T inverse as you are adding.
It's not true even. That's new to me. I thought it was an open question.
Yeah, that's what I mean. I understand that. I mean, I found this on, I think, Math Overflow or something, that somebody had given an example that of a coherent ring such that the polynomials over it is not coherent.
But I'm talking about regular coherent. Are we talking about the same notion? Regular coherent means that.
You are in regular to it. Yeah.
Okay, this is new to me. I thought I was also Googling, and I thought it was an open conjecture. But it's good to know because then we can justify why we had to do all these difficulties.
The concept of supercoherence was invented precisely because.
Yeah, sure, exactly. Yeah. But I didn't know that there wasn't counterexample to this. That's new to me. If you can tell me the reference, would be great.
Okay. I look it up.
Yeah.
But it's not what T and T inverse, just T.
Just T.
Yeah.
Okay, for us, we only need this.
Yeah. So, yeah.
Or for R of T, okay, that I do not know. I've always thought about TT minus 1.
Okay. So, given that we are already past 11, if there are no more questions, I will stop the recording.